In this example, we're going to do a hypothesis test when we have two independent samples. So in a clinical trial of Lipitor, 94 people were treated with Lipitor and 270 of them were given a placebo. Of those treated with Lipitor, 7 had infections, and then those given the placebo, 27 developed infections. So we're going to test the claim that the rate of infection was actually the same for the two groups using a significance level of 0.05. So in this video, we'll test the claim by doing a formal hypothesis test. And then in the next video, we'll test the same claim, but we'll use an appropriate confidence interval. So to test the claim by hypothesis test, the first thing that we're going to do here, or what I recommend that you do, is highlight or underline the original claim that you're trying to test. So here that claim is that the infection rate is the same for the two groups. So next we need to ask ourselves, what are the two groups? So down here, I'll call the first group population 1, where population 1 represents the group that's given the Lipitor. And then I'll call group 2, I'll call that population 2. And population 2 will be the group that was given the placebo. Okay? Now, if we go back to the claim, we're testing the claim that the rate of infection is the same for the two groups. So when I see rate of infection, this right away lets me know that we are looking at the parameter proportion. So we're dealing with two population proportions, okay, where we usually identify the proportion as P, and P represents the infection rate for each group, okay? And so an infection rate, we can represent that as a percent, or you can write that percent as a decimal, or we can simply show that rate as a ratio or a fraction, okay? All right, so knowing that we're dealing with a population proportion P, we'll call P1 the infection rate for the Lipitor group at the population level, and we'll call P2 the infection rate for the placebo at the population level. And then this original claim is claiming that these two rates are the same. So that means I'm going to use the equal sign, and then I'm going to keep track here that this is the original claim. So right away, I know that this original claim is going to be my null hypothesis. So I'm going to go ahead and start doing the hypothesis test, and I'll write it down in steps. So the first step is to write down your two hypotheses, the null and the alternative hypothesis. So here, the original claim is that P1 is equal to P2. And then again, keep track of the original claim so you know how to state your final conclusion towards the end. So then what is the alternative hypothesis going to be? The alternative hypothesis is the statement if the null hypothesis is not true. So if the infection rate is in fact not the same for the two groups, that means that either the infection rate for the Lipitor group is smaller than the infection rate for the placebo group, or the infection rate for the Lipitor group is greater than. But we need a mutually exclusive statement, so I'm going to write down that P1 is just simply not the same as P2. So I have a mutually exclusive statement from the null hypothesis. And this also lets me know that I'm going to have a two-tailed test. So I like to draw the bell-shaped curve on the right here just so that I can visualize this hypothesis test. Typically, students will skip this step once they are really comfortable with doing a hypothesis test, but I will show the visual when I'm making these videos for you. So let's take a look at our sample data. So in order for me to test the claim, I need to gather some evidence, some sample data. So the sample data that we have to work with is the group with the Lipitor. Our sample size was that there were 94 people, and of those 94, so X represents the number of people who actually developed infections. So that's 7 people had infections. This is going to give us our p hat value. So I'll call this p hat sub 1, which represents the infection rate for that Lipitor group. So that's 7 out of 94, or an infection rate of 0.074. So this represents the infection rate for the Lipitor group. Okay, and now we need to see what's going on with the placebo group. So I'll call this N sub 2 out of 270 people. X sub 2, 27 of them developed infections. And so that gives me a sample proportion, we'll call this p hat sub 2, of 27 out of 270, or an infection rate of 0.10. So the infection rate for the second group is 0.10. So just looking at our sample data, hopefully you can see right away that, right, the infection rate for the two groups is in fact different if we're just looking at our sample data, because clearly 0.074 is not the same as 0.10. In fact, if we calculate the difference, we can see that that difference, let me choose a different color marker here. Okay, so if we look at the difference, so the difference between those two sample proportions, p hat 1 minus p hat 2 is 0.074 minus 0.10, which gives me a difference of negative 0. What is that? 0.026. So again, we do see that there is a difference in the two infection rates. But the bigger question that we always want to ask in statistics is this difference statistically significant? Is it is the difference large enough for us to say that the infection rate actually is not the same for these two groups? Okay, all right, so the only way that we'll know if it's statistically significant or not is if we actually do the hypothesis test and see where it falls on this bell-shaped curve. So if that difference falls in the tail, okay, then that means that the difference is significant. But if the difference does not fall in the tail regions of our bell-shaped curve here, then that means that that difference is not significant, meaning that the infection rate for the two groups is actually the same. Okay, and so any differences that we see from our sample data is just due to chance because of sampling error. So in order for us to figure out if that difference is statistically significant or not, we're going to have to calculate the test statistic for the difference in our two sample proportions. So the test statistic is going to be a z-score for our p hat 1 minus p hat 2 value. Okay, all right, so how do we calculate this test statistic? You can either use the formulas given for this chapter, or you can use your graphing calculator. So I'm going to use the graphing calculator for this video. And so because we're dealing with two independent samples and we're looking at proportions and we're doing a hypothesis test, you're going to choose the option 2 proportion z test. So 2 because we have two independent samples, proportion, and then we always use a z test, okay? All right, so when you do that on your calculator, it's going to give you a z-score or a z-value of negative 0.73, and it's also going to give you the p-value. So I'm going to go ahead and write down the p-value here, and that p-value is 0.464. Okay, we are going to use either this z-score or this test statistic. Okay, we're either going to use this test statistic or this p-value to make a conclusion about the null hypothesis. So let me show you visually what this test statistic of negative 0.73 and this p-value, what it means on this bell-shaped curve. So on this bell-shaped curve, we've got at the center 0, where 0 means that there is no difference between the two infection rates. So P1 is equal to P2. That's at the center because if we look at the difference, if they are in fact the same, then P1 minus P2 clearly would be 0, okay? Now, if the infection rate is, for the Lipitor group, is smaller than the infection rate for the placebo group, then we'll see that it's going to fall on the left tail of this distribution because that's where P1 is less than P2. Their difference is going to be a negative number. So our sample data here shows that the difference for our sample data is negative. So we expected this test statistic to be a negative z-score, and it's going to lie on the left tail of this distribution. So where exactly do I plot it? I need to put some more numbers on this number line. So this is 1, 2, and 3 standard deviations above the mean, -1, -2, -3 standard deviations below the mean. And then we can see here that negative 0.73, which is our test statistic, lies right there. Okay. All right, but I need more information here. So you have to ask yourself, okay, well, what does that mean? So it goes back to your significance level. Since we're testing at a significance level of 0.05 and we have a two-tail test, This means that our critical region is going to be in the left tail and the right tail, where that significance level is split equally. So if I take alpha and divide it by 2, 0.05 divided by 2 means I have a critical area of 0.025 on the left and 0.025 on the right. So in order for me to know exactly how much to shade in the tail, I need to figure out what is the critical value that corresponds to an area of 0.025 in the tail. So you can use inverse norm for this to calculate that critical value. And so if you do that, it's going to give you a critical value of negative, so I'll mark it on here, negative 1.96. And again, because this is two tail, right, I'm going to mark the positive 1.96. So these are called your critical values. So critical value. And these critical values define the critical region. So the critical region is where we're going to find test statistics or z-scores that have very, very small probabilities of occurring. Okay, so on the right tail here, that has an area of 0.025, and then on the left, the area of that red shaded region is also 0.025. Okay, so making a conclusion, that's step 4, making a conclusion about the null hypothesis. If you're using the test statistic, right, so that value, negative 0.73, I hope you can see in the graph here that test statistic does not fall in the critical region, meaning it doesn't fall in the tails. So that means that even though we see a difference in our two sample proportions, that difference really isn't significant enough for us to reject that the difference between P1 and P2 is 0, meaning that, right, we don't have enough evidence to warrant rejection of the claim that the two infection rates are the same. So we would say that we would fail to reject the null hypothesis, and then always make sure you explain how you know. So if you're using the critical value method, I know this because the test statistic, which is that value z equals negative 0.73, does not fall in the critical region. Okay. All right, and you can stop there. But I'm going to also talk about how you know to also fail to reject the null hypothesis if you're using the p-value method. So visually, I'll show you on the graph here, the p-value represents the area that I'm about to shade in green here. So the area shaded in green, and again, because this is a two-tailed test, I'm going to have to mark it on the left-hand side and on the right-hand side. So I'm going to mark on the right-hand side where 0.73 is, and then shade in that area to the right. This green shaded area is the probability of getting a difference in our two p hat 1 and p hat 2 values, right? Or a value that is at least as extreme as the one that we got from our sample. So you can see here visually that this p value is relatively large. In fact, it has an area of 0.464, which is approximately 46.4%. So there was a 46.4% chance that we would have seen a difference similar to the one that we got in our sample. Therefore, the fact that we saw a difference, that was just due to chance, not because there is a true difference in the two infection rates. And then hopefully you can also see visually that the total green shaded region in the graph is much larger than the total red shaded regions. So if you're using the p-value method, so let me just write down here, I can also come to the same conclusion that I would fail to reject the null hypothesis, right? But this time my explanation will be that it's because the p-value is greater than the significance level. Okay, so 0.464 is clearly greater than 0.05. And so then the last step, and I'll write it down at the bottom here, is to actually interpret your results, state the final conclusion. So because we failed to reject the null hypothesis, and remember, I'll highlight here in yellow, that null hypothesis is also the original claim. So we're saying that we don't have enough evidence, right, to warrant rejection of that claim. So I would say exactly that. There is, oops, let me use my pen, not my highlighter. So we would say there is not sufficient evidence to warrant rejection of the claim that the rate of infection was the same for the two groups. So next, I'll show you how to test this claim with the appropriate confidence interval.